Hey everyone, and welcome. Today, we're going to tackle one of the biggest hurdles in organic chemistry, those infamous name reactions. But here's the twist. Instead of just memorizing a bunch of steps, we're going to unlock the actual logic that makes them tick. And we'll be using the famous aldol condensation as our guide. So let's just dive right in. You know, the biggest problem in OChem usually isn't forgetting a reaction. It's staring at a super complex molecule and having absolutely no idea where to even begin. The secret, the real trick, is learning to see the set, identifying the key players and what they're supposed to do. Once you see that, the path from question to answer just snaps into focus. So, the big question is, how do we find this hidden logic? Well, it turns out that a lot of these really intimidating-looking reactions are all governed by one surprisingly simple and really powerful principle. And today, we're going to pull back the curtain and show you exactly what it is. All right, our story starts with the main character in so many of these reactions, the carbonyl compound. To really get what's going on, we have to understand its core chemical personality. Okay, so here's the central problem. That oxygen atom is super electronegative, which is just a fancy way of saying it's incredibly greedy for electrons. It hogs the electrons in that double bond, pulling them all towards itself. And that leaves the poor carbonyl carbon really electron deficient. You can think of it like a chemical pauper, just desperate for some electrons. So what do you think happens when you try to react our electron-poor carbonyl with another electron-poor species, like an electrophile? Absolutely nothing. It just doesn't work. A pauper can't help another pauper, right? They both want the same thing, electrons, so they've got nothing to offer each other. No reaction. And this is the big aha moment. If our carbonyl pauper can't do the job on its own, what if we could just transform it? What if we could take our electron-poor pauper and turn it into a fabulously electron-rich prince, totally ready to go on the attack? And guess what? This transformation is incredibly simple. First, we just add a base. That base comes along and plucks off a proton from the carbon right next door to the carbonyl. We call that the alpha carbon. And that one simple move creates a brand new, super powerful species, the enolate. I mean, just look at this change. It's night and day. We go from a carbonyl, our electron pauper, a pretty terrible nucleophile, to an enolate. This thing is just swimming in extra electron density. It's our chemical prince, a super nucleophile. It's ready for action. So that's what an enolate is. It's the negatively charged, super electron-rich version of our starting carbonyl. And it's the absolute key that unlocks this entire type of reaction. By creating it, we've basically made the powerful attacker that we needed all along. Now, I know what some of you are thinking. What about the enol? Isn't that electron-rich too? And yeah, it is, but there's a huge difference in how reactive they are. Think of it this way. The enol is like a garden hose. It's got some water pressure. It can get the job done, eventually. But the enolate, that's a fire hose. It's way more powerful and gets the job done fast. For this reaction, we're not looking for good enough. We're looking for an absolute powerhouse. Okay, so we've got our electron-rich prince, the enolate. Now let's see what it can do. It's time to watch it in action in its most classic story, the aldol condensation. Now, the aldol reaction comes in a few different flavors. First up, you've got the self-aldol, where an enolate attacks another molecule of its own kind. Then there's the cross-aldol, where you use two different carbonyls. And finally, the really interesting one, the intramolecular aldol. That's where one part of a molecule forms an enolate and attacks another part of the same molecule, snapping together to form a ring. We're going to focus on that last one, the intramolecular version. This type is a total favorite on exams because honestly, it looks really complicated. But the truth is, it's perfectly logical, as long as you have the right strategy. And this is the exact question that trips everybody up, right? You're looking at this big molecule, it's got multiple carbonyls, multiple different alpha protons you could pull off. So which one do you choose? Which carbonyl does it attack? Which of the possible rings is the right one? It can feel a little overwhelming. Okay, forget all that confusion. I'm going to give you a simple checklist. 3 golden rules that will guide you to the correct product pretty much every single time. Let's break them down, one by one. First things first, ring size is king. Chemistry at its heart is all about stability. And when it comes to forming rings, not all sizes are created equal. The most stable, happy, low-strain rings are 5- and 6-membered rings. So your very first move is to look for a reaction path that can create one of those. I mean, just look at the difference here.
The stability of 5- and 6-membered rings is way, way higher than the smaller or larger ones. They are the thermodynamic sweet spots. So if one pathway gives you a 6-membered ring and another gives you a 4-membered one, well, the choice is a no-brainer. You always go for 5 or 6.
Okay, rule 2. That initial aldol addition reaction is actually reversible, which isn't great if you want a stable product. What really locks everything in place is the final condensation step, where the molecule kicks out a water molecule to form a nice, stable double bond. But for that to happen, there's a crucial requirement. And that is, the alpha carbon that you deprotonate in the very first step must have a second proton available. Think about it. You need one proton to get yanked off to form the enolate, and you need a second one that can be removed later for the condensation step. So if a potential alpha carbon only has one hydrogen on it, it's not going to work. It can't give you that stable final product. And finally, rule number 3. If you followed the first 2 rules and you still have more than one option, the enolate is going to take the path of least resistance. It's always going to attack the carbonyl group that's less crowded or less sterically hindered. It's just easier. An aldehyde, for example, is a much easier target than a big, bulky ketone. So let's just zoom out for a second. We've just broken down a pretty complex-looking reaction. But the real goal here wasn't just to solve this one problem. It was to help you build a whole new way of thinking about these puzzles. So this is your new toolkit, your mental model that you can use again and again. First, you spot the electron popper, the carbonyl. Then you bring in a base to perform that royal transformation into an electron prince, the enolate. Then you let that prince attack the best target. And if you're making a ring, you just run it through the 3 golden rules. Simple. And that, right there, is the ultimate takeaway. Mastering organic chemistry isn't about trying to memorize hundreds of individual reactions. It's about understanding the fundamental principles, this whole story of poppers and princes, of electron-rich and electron-poor, that actually govern all of them. It's a way of thinking that makes the complex simple. You know, this whole framework of transforming a reactant to unlock its hidden potential, it doesn't just apply to the aldol. You're going to see this exact same logic in the Claisen condensation, the Michael addition, and so many others. So the real question is, now that you have this key, what other doors are you going to unlock?